I'm very excited to have 4 research talks here. I'm going to switch it over to Guo, who I talked about a little bit already. I tried to make little intros, but honestly, in the 2 sentences that I could try and sum up the work done by these 4 faculty, I think it's probably better you just watch their drawings. Much more informative.
Let's start.
Go ahead. Yes, please.
All right. Well, thank you very much. I'm probably the oldest one since the beginning of this car seat business, and I was hired, as a matter of fact, partly supported by this sister center who got a lot of money from Maui project, and so they said, well, they want to strengthen the computational aspect of the research, and so I was hired under that auspice. And so I've been here since 1998 and chemistry faculty, and we've been doing exclusively computational studies. So without CARSI, I think none of this is going to be possible. So I really appreciate this. All right, so here is sort of a rendition of what's going on, and we have essentially interest around chemistry, right, from all sorts of things you will hear, and we're doing computational studies and trying to figure out what is going on, right? So, so let's first of all look at the temperature scale, because the title of my talk is going to be from very cold to very hot. And so what are we talking about here? We have ultra cold that's approaching absolute zero, right? And now it is possible to actually prepare molecules in that regime. Of course, we have very hot regimes as well, and so what I want to sort of get to the point where all these things are related. Okay, so the computational approach can be applied to a very wide range of phenomena. And on the cold side, we have something called the Broglie wavelengths, and so people who actually know quantum mechanics knows this very well. So you have essentially a wave characteristic of all the molecules behave like wave at very cold temperature. Okay, and so you have other quantum effects such as interference, tunneling, and all these things at very cold temperatures. And so that's very important for us to understand fundamentally what is going on, especially in light of recent interest in quantum information science. Okay. And so in 2021, I believe, a Nobel Prize in Physics was awarded to several people in Gila up there in Denver border on the so-called Bose-Einstein condensate, very low temperature. And so that actually opened the door for all sorts of possible research, especially on the quantum effects in chemical processes. And so I will talk about one of them. Right. At very high temperature, we have, of course, things like hypersonic processes, right? So you have, let's say, a module which is fly down, retrieve the 2 astronauts from the space shuttle, International Space Station, and you have to come back. And when you come back, they have to come in at very high temperature, very high speed, and actually cause a very high temperature. And the question is, okay, how does this actually hold up the return module? And of course, there are a lot of heat shield materials on the other outside. And we're also interested in several ongoing projects in NASA. Atlas is one of them, going to the moon, but they have to return, right? And other one is called the Dragonfly that goes to the Titan, a satellite of Saturn, and have the very interesting chemical composition because they have a lot of methane lakes. And so the question is there any interest hint on the origin of life and so on? Okay, so let me tell you a little bit about chemistry. All right, and not about a movie. Okay, so but anything that we do here is related to something called the Bohr-Oppenheimer approximation. So essentially, what we do is to separate the motion of electron because electron moves so fast compared with a nuclei, and actually we can solve the electronic problem, and then we got these points at different geometry of the molecule, and then we can actually use machine learning to map out a continuous potential energy surface, like the landscape in New Mexico, right? You go to Sandia and, you climb up and what is the way to do that and so on and so forth. And of course, this separation of electronic and nuclear motion is due to these two people, Max Born and Robert Oppenheimer. How many people have watched that movie? Very interesting, right? New Mexican scientist, that I would say that he was the postdoc Max Born and Göttingen. And the two actually come up with this idea and formed the foundation of today's computational chemistry, right? So let's take a look at the latest achievement in cold chemistry. And now scientists can cool the molecules, the atom molecules, to 10 to minus 6 Kelvin. So it's very, very close to the absolute zero. And they can also prepare these molecules at whatever quantum state they can actually you want to put it in. So this is a scheme that allows you to go from this super cold atom to form molecules. And this molecule that they have worked out is called KRB. Okay, this is the molecule that they actually, sort of workforce that they use to, they want to do quantum science, quantum information science, right? They do quantum computing and so on and so forth. All right, and so they can prepare these things in all these kind of states. Quantum states use lasers and ultra cold sort of a technology, right? And so once they do that, they have these tens of thousands of these molecules in a trap, right? And then they watch this thing because they want to study the transition of these molecules to the excited state and try to use that as a quantum computer. But all of a sudden they find it's very difficult because these molecules start to get out of the trap, right? And they got lost. And so you can see the decay curve, and there's rate coefficient that you can actually plot out. And so these are sort of detrimental to the quantum information science, and we need to figure out what is going on, right? And so it turns out there are two, I don't have a pointer, but do you have it? Oh, perfect. Okay. As you can see here, if I prepare two molecules, all the molecules in a particular quantum state, and that actually shows as a boson, right? And so these things just disappear very quickly. You can't even see them. They just prepare them, they just go. Or you can prepare them in something called fermion, okay, so half spin. And this one is limited by what we call a P wave. It's just the wave is scattered, right? All right, and then they actually decay as a function of temperature. Here's a microkelvin. It's very, very low, right? And so the question is, what is going on here? So it turns out when you prepare this fermion, you form a potential barrier, and these things can get trapped into something else, right? And so that's what is going on. So here is our work, and we can actually map out what we call the potential into surface, follow the recipe of Born and Oppenheimer. And these are all the structures. So you can see there are a lot of wells, a lot of saddle points, a lot of peaks, and so on and so forth, just like the landscape in New Mexico, right? Okay, there's a blue hole and everything. Okay, so you can actually have the potential. They can calculate the scattering of these molecules, and turns out they actually react, right? So here are two KRB molecules, and they can actually trap into something in these wells, as you shown here, and eventually escape right down there, right? And so it's a very small window you can actually escape, and that is why these things start to disappear. And there's a barrier, it turns out, in the front, and you can actually calculate with Carsey computer, all right? So that's cool. And here is exactly what happens. We have calculated these points, these lines. These are external data obtained in GILA, and here are some of the other ones. And you can see we follow very, very good with that. And so what happened here is really something very interesting. And that is when you go through this barrier, right? It's like through a baseball over the window, right? In the classical world, you can either break the window or bounce it back, right? In quantum world, there's certain probability this baseball is going to penetrate the glass and go to the other side. And that's what we call tunneling. So it turns out tunneling usually happens in very light atoms like hydrogen, deuteriums, and things like that. But here we have very heavy molecules. And how the heck does it actually tunnel through this barrier? Well, it turns out when you get to very, very cold temperature, these things become a wave, right? So you imagine a wave of light through the window, you can actually penetrate some of them reflected. So this is really cool quantum effect. All right. So we can actually calculate the final state distribution. These are the experimental data obtained at Harvard University, a very sophisticated experiment, and we can actually predict what happened. Turns out we did predict what happened. They have tried several times before they can get the right answer. So this is very cool, right? So this is published on Nature, and I think that will make Ellen very happy. Okay. All right. So now off to very hot regime, right? So we have, as we have seen, that these return modules can come down to the Earth will carry human beings and so on and so forth. So you have to make sure that they don't burn off, right? And so what happened is that this is the typical process that these things can hit the surface, very high temperature, and the temperature in the shock front can go up to 10,000 or even higher Kelvin, and that causes all sorts of problems, right? So, and we have essentially talking about high temperature or hyperthermal chemistry here. This is a picture of SpaceX rocket, and you can see these are tiles, right? Very lightweight tiles, and it's made of carbons, right? So we don't know exactly what they are made, but we know they're made of carbons. And then the nitrogen, the oxygen, the atmosphere start to dissociate because the temperature is so high. They even actually lose their electrons to form plasma around these spacecraft. And so you lose communication, right? It used to be space shuttle come down to New Mexico, right? And so when they enter the atmosphere, they lose communication completely for about 20 minutes, right? So we need to know the chemistry here, and these chemistry are vital in guarantee that these things are safe. And so we have a NASA center called Access, and that is restricted. All right, okay. So another project that we're working on also with NASA is the Dragonfly project, and we can send a drone to Titan, okay? And again, you want to make sure that these space modules are safe to land on the surface because it's a very dense atmosphere, but it's instead of made of nitrogen and oxygen, it's actually made of nitrogen and methane. So lakes, methane lakes on the surface. And so that's something that we need to make sure. So we have a center, computational center with about 10 schools around university, around US to do that. And happiness is one thing that people probably have learned, that they actually go to the moon and trying to figure out what's going on and come back. And so have to endure the high temperature when you return to the Earth. So what do we do computationally? We want to know, how these dissociate molecules react with the carbon materials, right? So you have these heat shield, and how does that actually work? And so it turns out oxygen atoms have two flavors, and one of them called triplet state, which is much more stable than the single state. This is the excited oxygen. And so we need to know when they actually scatter out of graphene, for example, right? How does that work, right? So you can prepare these atoms and let them actually dissociate. You can actually react from this blue line of potential into surface or the red one. And so they can actually cross as well. And so we have collaborated with a Göttingen group who measure the angular distribution, right? So this is the experiment angular distribution. This is the angle, this is the speed, and so on and so forth. And our data for different models, this is the adiabatic, this is sort of triplet, we can actually see which one is closer to the experimental data, and that seemed to be closer to reality, right? So computational study is very important for that matter. We can do the potential into surface, use machine learning, and do trajectory scattering, and so on and so forth. All right, so let's look at another project, which is the atomic nitrogen. So atomic nitrogen also have two flavors. One is the ground state nitrogen, which does not react to, is almost nothing. And here's the excited state, which is very reactive, right? And so when you form these things, they can actually cross. This is the doublet D. This is the excited state, and it can come down and cross with this red curve and come down to be the non-reactive part. Okay, and so how does this happen? What is the rate coefficient for this process? Is very important for monitoring, to simulating these processes, especially when coupled with the fluid dynamics calculations, right? And so we can calculate these things, and by mapping out the potential and do trajectory calculation. Here's a map of these potentials, and these are the crossing points. You can see they can actually come down in various geometries and cross to the red one, and then come back to something that is non-reactive. And so we calculate something called the rate coefficient, which is how fast this reaction takes place. This is the WD going to quartet S by colliding with CO. And you can see our calculation. There are two different calculations, and there are two different sets of data. And this is the more reliable calculation. This is the more reliable experimental data. Okay, experiments can be wrong too, right? So, all right, so it seemed to work out really well, so we can predict. And the nice thing is that they have done this measurement at room temperature, but in simulation, they have to be very high temperature. So how do you know that you can use this one to predict what's going on at very high temperature? Usually not, right? But theory can, right? So you can actually validate that at low temperature or predict high temperature reaction coefficients. So, all right, with that, I'd like to conclude. I'm proud to be a chemist, okay? It's central science, and actually branch out to various things at very low temperature. We can actually connect that to quantum physics, quantum information science, astronomy, and so on and so forth. At room temperature, we're going to hear stories, of course, using computer to do biology, medicine, and so on and so forth. All right. At high temperature, and of course, chemistry can deal with, as I just talked about, space exploration, which has become a very hot thing in New Mexico as well, and fusion and combustion and all these great stuff. And the theory of computational chemistry play a central role because a lot of times we cannot afford to do all the experiments. Sometimes these experiments just, you have one chance, right? You go to the Mars, that's the one chance you have. And so how do we make sure these missions are safe and so on? And so we have shown you, hopefully convinced you that we have used different computational approaches to span 10 order of magnitude in terms of temperature. Okay, high performance computing, of course, is the key, right? Without which we cannot do. Right. So let me thank CARC again, which is really an asset at UM. It allows us to get funding from all these funding agencies, and these are my student postdocs. It's a small list, as Matthew can attest, and some of my collaborators. Thank you very much. I'll be happy to answer any questions you have. Yeah, I'm perfect. Thank you very much.
I know if Susie was here, she'd have lots of questions.
I know. Right. Thank you.